You don't see that, but it's crowded with the Leiden University people. And we're welcoming today actually Simone from South Africa, but also Professor Craig Sheridan. And he is visiting us live. So it's not only across all the continents, but also live in Leiden that he will present his work. Just to give a short introduction on Craig, I say. Sorry. He did a bachelor on chemical engineering on Wits University. And then he worked, he did an MSc on wine biotechnology in Stellenbosch University. And then he worked in industry as an environmental consultant for a couple of years. But he got back into academia, I would say. Also co-founder of an industrial and mining water research unit, and the founder and the director of the Center in Water Research and Development, which was rebranded to Wits University. He gives a lot of different lectures also related to water and society. And currently he oversees his research on mine wastewater through the lens of circular economy. So extracting critical materials. And it's all the time related to working on water security, especially in South Africa. So I hope that you like the to give an applause to our visitor and that he can give his lecture to us.
Okay. Hi everyone, and hi everyone online as well. I am closing that. Right. Okay.
It's unmuted.
I'm muted.
Yeah, that's good.
Great. Okay. Wow, that's loud. Okay, so today I'm going to be speaking about valorizing wastewater and what we're doing and how we're thinking about some of our environmental problems that we have in South Africa, one of which is mine impacted water. So the Netherlands is not really a mining country, but you are a water country and a wet country. So hopefully we've got some areas of like commonality or overlay. This picture that you can see in the screen is a typical mine impacted water stream. Globally, there are many of these things. They look like this. They occur often co-located with mining companies or mining houses or mining industries. And we're going to talk a little bit about what that is. I'm just checking if I can. Right. So I'm going to talk about how this project forms part of our larger research program and how we start to reframe these problems into opportunities for us to think about. This is a project that we're working on currently. Our partners are the University of Copenhagen. You probably know them, they're fairly close to you. And the University of Stellenbosch was our other partner. And we have 3 SMMEs, small companies that do different things, and we can chat about them as well. Okay. And this project is primarily funded by the Danish International Development Agency, DANIDA. Right, so what is mining influenced water? Really what happens is that you have a previously large concentration of, or large amount of rocks, which have suddenly been exposed to the combination of air and water when you start to expose these raw rock surfaces, which happens when you mine. And it leads to oxidation, typically of the sulfide minerals, and it releases sulfates and metal into the water. So they're the main requirements for mine impacted water, but there are also some other factors at play. So the primary things that we see are that you need water, you need oxygen, and you need this metal sulfide. And what you end up with is a lot of sulfate and a lot of metal plus. Typically, in this instance, it's iron 3 plus. But you get a lot of other things like calcium, magnesium, aluminium, magnesium. And where we're quite interested is some of these things like rare earth elements or the critical elements. The chemistry is not particularly complicated. It's a series of chemical reactions which are either or not microbially mediated. So you often have bacteria which will enhance, they eat the sulfide and they can catalyze this reaction. But really what happens, which is the real issue with this, is when you look at the completed reaction, you form 16 H plus atoms for every FeS2. And what you do is that FeS2 cycles between ferric and ferrous, ferric and ferrous ion. I'm going to take this off. Sorry. Yeah, I speak loud.
We can also provide this one.
No, that's fine. I think everyone can hear me. Right. So this ion cycles between ferrous and ferric ion. And what happens is that it becomes a self-catalyzing chemical reaction as you have this cycling between ferric and ferrous ion, and you start to release more and more hydrogen atoms, which makes this a really complex reaction to stop. And the reason it doesn't stop is because of the cycling, and this can carry on for centuries. And we know this because not far from here is a river called the Rio Tinto. It's in Spain. There's a mining house called Rio Tinto, named after this area. They've been mining here for 5,000 years. So we know that this happens. That's what it looks like. And it flows red. That's what Rio Tinto means. And it's a legacy. It's from the Tartessians, the Iberians, the Phoenicians, the Carthaginians, and the Romans. They mined this area and they continue to mine it to this day. So this river has endured continuous contamination for millennia, driven by both natural processes and human mining activities. But it's not just related to areas like this. If we have a look at the globe, these red areas are where we see acid mine drainage. So both the US and Canada, a lot of South America, South Africa is the bottom tip of Africa, that little country there. And there are many, many sites like this across the globe. So we know that this is a massive environmental opportunity, not an opportunity, a massive environmental issue, but it has also a lot of legacy challenges associated with it. The mouse is gone. That's okay. Okay. So in terms of the project that we started working on, we had a look at this. The people online, I'm apologizing. I can't see my, there's my cursor. 1 second, and I'm going to put on the pointer on the screen so you can see laser pointer. This is a project that was funded by Danita. And what we had to look at was we said, how can we start to see this as a sustainability opportunity rather than a very long-term environmental liability? So what we have is we have acid mine drainage. It comes into a process of some sort. We said, what could we do with it? So we said, maybe we could do some ion exchange, strip out the value. We take out things like high value rare earth elements. We then have low value AMD. What could we do with acid? Turns out acid is key to acid hydrolysis of cellulose if you want to tap into second generation biofuels. Maybe we could do some of that. We could then generate an organic residue. Could we then do some enzymatic digestion and fermentation? And it turns out actually we can get glucose out of this process and go across to ethanol. Turns out it's not necessarily a sensible pathway. It's actually far more useful to break the cellulose a little bit and then to biodigest what's left and make methane for an alternative energy source. And then at the middle here, we have this iron-rich sludge. And the idea is that the sludge you could then do something with, like refine maybe. Should I use that? Okay, cool. Great. Okay, so the issue with this is that you have to start co-locating different substrates and different products within where you're working, because it makes no sense if you're trying to find some sort of like bio feedstock that's located 400 or 500 kilometers away. So obviously you have to have everything co-located at your site. And in this instance, we were able to do that. So let's just focus. I'm going to segue around this because I don't want to talk about biodigestion that was quite interesting. But I really want to talk about the critical raw materials recovery and focus on our successes and maybe some of our challenges in this space. The critical raw materials are listed as critical primarily because they're critical for our Western way of life. They're listed critical primarily in many instances because China is the sole provider of these substances. So when you're looking at things like rare earth, most of your rare earths are coming from China. And of course, this is a geopolitical risk, having a sole supplier in a country which we're not necessarily 100% friendly with. Not South Africa, other countries. We're friendly with everyone and no one at the same time. But other countries are friendly or not friendly. So we were looking at around what technologies could be applied to using to extract these rare earth elements. And I'm going to go through some of this. So one of the things we thought was, let's try and see if we can use ion exchange techniques. And we had a look at resins, and could we actually use these resins to extract some of these rare earth elements from this waste stream? And this is all around the circular economy thinking. If I go back to this, you start seeing the you've got this wonderful EU diagram showing what circular economy looks like, where you go from linear production systems into circular production systems, where you're thinking about cradle to cradle production. But that's for new products. And actually, that's really difficult to implement on an existing capital intensive industry like a mining facility, where typically you can't do a lot with your waste products anyway. They sand at the end of it, or very small particles of silica. So we were saying, how can we apply the circular economy thinking into this context? We have this existing legacy, and that's what we were doing. So we said, first of all, what are the places that we're finding this acid mine drainage? Now, this has got a lot of animation, so I hope I get it right. But what we did was we first tried to see where is the AMD located. And it looks from this animation, and I have my postdoc, Tamla Naidu, to thank for this presentation. She does a wonderful job. But really what you can see is this is co-located across quite a large geographical area. And we're talking that map that you saw is about 200 kilometers from east to west. So it's a large area. We have a lot of coal in South Africa. We still have coal reserves. This is not a good thing, but for a couple of 100 years. So we have a lot of power stations, coal-fired power stations. We have a very large facility which uses the Fischer-Tropsch process to create fuel, petrol from coal as opposed to from petroleum oil. And it means that we have a lot of legacy sites with a lot of tailings facilities, and we have a lot of potential for acid mine drainage or acid generation out of these things. So our first step was to say, what is in this acid mine drainage that we're seeing? And this pie chart shows you that mostly we're seeing cerium. And then we have a little bit of some of the other lanthanates. We have some yttrium, we have prantium, and we have neodymium, and we have a whole bunch of other things located from uranium, thorium, and I wish I could remember the names of all of these ones. I can't, I'm sorry. But this shows you our relative abundance of these minerals. But what's far more striking is if you look at this in context of what we're seeing. So our rare earth elements, I don't know, can you see visually there's a little red line down the center of the screen here? That's the small sliver that they comprise of the entire spectrum of this mine drainage, which is primarily iron and magnesium. So of them, cerium is the most abundant, but actually really what we're seeing is a primary source of iron. Depending on where we go, this iron can be as high as 3 grams per liter. And in other contexts, we can find sulfate in up to 15 grams per liter. So these are not micropollutants. We're not chasing the picograms or the micrograms per liter. We're looking at grams per liter of contaminants that are actually entering into our environment. So this is quite a large environmental problem for us. So in this graph, I show you some of the different concentrations. You can see iron in this AMD was 4 grams per liter. Magnesium is 477 milligrams per liter. And it goes down to uranium, which is 0.03. There are still uranium sources adjacent to tailings facilities. In fact, in Johannesburg, there are upwards of 70 milligrams per liter. So there's a lot of uranium around. Most of our ore bodies are uraniferous. So we're aware of this. And it also poses a little bit of a challenge with the handling of our residues. We don't want to trigger the nuclear non-proliferation treaties by enriching uranium by accident in our laboratory when we're actually trying to do an environmental good. But really what we're interested in is these things here, the yttrium through to thorium. These are high value products. They're actually very valuable. The economic value is significant. So removing iron is key. What do we do with this iron? For any of you who've worked in water treatment, you'll know that iron is one of your precipitants that you use to actually treat the water in your drinking water. So as soon as you start to remove it, you tend to knock out all of these other things at the same time. So we're having to think really carefully about how do we selectively remove either the rare earth elements or the iron first in order to not co-precipitate. This is a graph showing a heat map. Again, we saw that earlier on, and I think if I tap it, there we go. So what we see is how the concentration of AMD varies across these different mine sites. In that map, you'll see that there's those little gray areas are typically these tailings dams. They're crushed rock to minus 75 microns, or they fly ash. Ion exchange is a practical technology, and typically we would want to use a resin. Please don't ask me about microplastic pollution in the context of my resins, because I'm going to say yes. Okay. It is a microplastic. They're typically polystyrene beads. We'll get into that now. But we're starting to have to think quite pragmatically about this risk. You know, we want to get these things out. We've got to use a technology. Actually, resins work quite well. So the test work we've done is having a look at some of the chemical similarities of these rare earth elements. They share coordination numbers and oxidation states. We also want to understand which is the right resin to use in the context. And we also want to look at how do we adsorb and also desorb these things. I've spoken about rare earth elements and critical rare minerals. They seem to be changing their name quite regularly, so I use that interchangeably. But one of the things we're also starting to pick up in some of our acid mine drainage sources, for instance, is arsenic at quite high concentrations. So that's really toxic, but it's also quite valuable as a critical rare mineral. So, you know, this may be a next thing that we're looking at, is how can we extract it? Once again, it's really bad for the environment, but it's quite useful for humans to use in electronics and things. So we had a look at some of our test work was in comparing the absorption fractions. And these are the tests for different resins. So just push the minutes. Doesn't work. No, it's fine. It's fine. So what we see is that this S108, which is the sulfonic acid resin, we found that we had a really good rare earth element absorption and fairly poor iron absorption. And that's what you want to get from these rare earths, from these resins. You want to selectively strip out the rare earths and leave your iron behind. So we tested all of these different things. For instance, this POH1 was quite good at iron removal, but not very good at rare earth element removal. So we started with testing all of these things. And what does it look like? So that's typically what our resin beads look like. That's in a shot bottle cap, little black resin beads. And what it actually looks like is a sulfonic acid group attached to this bead. And what you're able to do then is this H+ atom over here is typically what you strip off the resin and you replace that with a metal. I don't know how much on ion exchange you've done, And that's an M plus, H plus exchange. And if you've got M3 plus, for instance, you would have it doing something like that. So you'd have triple the activation and you remove that. So we had test work. So this is what it looks like before. I have a jar of this in my office. If any of you ever come to visit me, I'll show this to you. It's really interesting. It looks like rooibos tea. So I'm sure you've all had rooibos tea. Please don't drink the rooibos tea in my office. It's terrible. But this is a before and after like visual. So you can see how effective these resins are at removing these, both the iron and the other compounds. The orange color is typically the iron. So we said, okay, this is great, but this is an equilibrium experiment. So what that means is you put it in a jar and you leave it for 3 days and you say, what's the answer? And we'd never work at equilibrium. We always work with kinetics because we don't necessarily have time. So we want to push things towards equilibrium as quickly as possible. So we then said, okay, well, how are we going to model this? And typically what we would do is things like isotherm models to describe how these resins absorb these minerals from the environment. The problem with this is that the maths gets a little bit complicated quite quickly. So there are multiple models. There's things like the Langmuir model, the Freundlich isotherm, the Temkin, the Dubinin, Radushkevich. And of course, then you can apply multiple regression techniques, like just Gauss-Newton or Bayesian or Newton-Raphson or nonlinear least squares modeling. And then you have to also figure out what your goodness of fit is on this resultant isotherm. And there are different ways of doing this. You can have residues, coefficient of determination or residual plots or root mean squared error, et cetera, et cetera. The issue with this is that these are typically single component techniques. When you start looking at 17 or 18 components, you start getting quaternary and nth degree interactions between multiple components. And it makes these models become quite complex. So we said, okay, what could we do? So we had a whole lot of different models and different forms. We tried different linearization techniques. You plot different things, and you can get a graph like this. So this is the residual plot for neodymium, I think, yeah. And that's your equilibrium concentration on the resin. And this is your equilibrium concentration in solution. So what this will tell you is how quickly you get from solution into your resin. And what's more important is we did that for everything. So you don't need to worry about those. But just to show you, we did them for all 17 of those compounds, as well as for iron and magnesium. And then we had a look at how good was the fit? How good was our modeling? And what's important is that, so iron and magnesium were not that good. Our modeling was pretty poor, but we think those are the lower value products. So we're not too worried about whether we're modeling them particularly accurately or not. What we were getting was very good modeling accuracy on things like yttrium and cerium, prentium, neodymium. These are the valuable compounds. So we want to make sure we're modeling these correctly in the context of this multi-component mixture. So we then said, okay, what are our activity coefficients? How good is this resin at removing this compound? And it turns out it's Tm, which I think is tellurium, is the best, and then it goes all the way down to iron. So again, this is good news for us. We want our resin to be selectively stripping out these rare earths in preference from the iron. And that's the sequence. So it's Tm is better than Lu, holmium, europium, uranium, etc., all the way down to iron. So now we know what's the right order to strip these things out, what's the right resin, how do we do this? And we then went on to these column experiments. So we pass our acid mine drainage through a resin column. This picture on the right is not real. It is real, but it's not RMD. It just shows you how you can get these chromatographic separations through these resin beads as you start to strip things out and they absorb. So we wanted to see what would happen. So our test work looks at things like bed volumes and breakthrough curves. If you don't know what a breakthrough curve is, basically it's telling you after how many volumes, which is the amount of liquid that's flowed through the system, how long does it take before you start seeing your inlets coming with your outlet? So that's where you start getting breakthrough. And your exhaustion is at that point. So that's when your inlet is equal to your outlet. So nothing's really happening in your resins. So we did this with our two primary compounds. So we said, let's have a look at neodymium and let's have a look at iron. And we have, sort of from 4 or 5 bed volumes, we start seeing a little bit of breakthrough, and then it comes out at the end. And that's what you're seeing over there is where we see the breakthrough starting to happen. So in both instances, it's there. We had about 80% rare earth absorption before breakthrough. So what that's telling us is that this technology is effective. It can actually work. But what it's also showing you is that the iron comes into your resins too. But what we then did was we expanded this on the iron. And this is quite an interesting graph. And the reason this one's interesting is it tells you that after a short space of time, you start seeing breakthrough, but we weren't seeing this immediate tapering off behavior, this plateau. And what that's telling us, and this is really cool for us, is that as your rare earths carry on absorbing, they start to displace the iron that's absorbed onto the resin. So this is why you're seeing this increasing behavior with time. So the iron's now slipping through your resin entirely, and all the iron that was previously loaded is coming off as you're displacing this iron with new rare earth. This is the behavior we want, 100%. So that's great. So we knew we could now start stripping out these things, and we could also get out the iron. This is the desorption. This is the sad point, is we had to use EDTA, which is not particularly good for the environment. And we're well aware of that. But this is the technology, and it's where it is at the moment. And it looks like we can get our rare earths out, which is also fantastic. But there are some promising techniques for some not so harmful chemicals like citric acid, for example, rather than EDTA. So these are also important. These points 1, 2, and 3 tells you where your iron is coming out and where the rare earths are coming out in relation to the iron. This was about the desorption challenges again, and what we were seeing is that at different concentrations it comes out a bit later. So what are our future works and challenges? So the one is overcoming the iron. To enhance this rare earth purity, we need additional ion exchange steps. We still have this residual iron problem, and we're refining this process to try and achieve this optimal rare earth separation and purity. Value recovery, currently we're saying we're extracting about 94% of our rare earths. So this yields approximately $35 in value per 1,000 liters of treated acid mine drainage. Now, this is quite an important number, because when you're trying to treat the stuff in the field, so this is if you're a mining house or a mining company located east of Johannesburg, you're looking at an economic cost of about $20 to $30 to treat your acid mine drainage. And we're saying we can see the value in this. The economic benefit is already at $30 to $40 per cubic meter. So we're saying, actually, don't treat us. This is not a liability. This is an opportunity. It's a resource. You can actually generate revenue on an ongoing basis from a liability, but you have to stop seeing it as a liability. And it's really around transforming waste into value. And this is kind of like the whole research thrust of our group is reframing waste as opportunity. And it's not something we're particularly good at yet. We still see this as end of pipe. Okay, we've got a process, we make a product, we discharge our effluent to the environment, we have an externalized environmental cost, and hopefully someone else will pay that, not us as the company. Okay, that's the human condition. It's always been the human condition for the last 5,000 years, or else the Romans wouldn't have polluted the Rio Tinto. And we're saying, wait a minute, this is not the right way. If we're good engineers, what we should be doing, if we're good engineers and scientists, I want to reframe that actually. Our waste product should be clean water. clean water, because then what we've done is we've derived all the possible value we can get out of it, because all that's left is the water. And that's really what we're saying, is that today's waste middens are tomorrow's resources. And how do we start to think about our waste as that? Not everything will be like that. PFAS may be something that we have to just like lock up forever. But it's about a challenge of viewing every one of our waste products as an opportunity that we can actually commercially exploit. In exchange, we can provide clean water for the environment and for people. So that's really what my presentation was about. A localized context, quite different to what you do. But again, I think the concepts are similar wherever you are. It's around thinking about this waste problem and how do we reframe it as an economic opportunity for the benefit of us. And if we're really clever, we get clean water out of the process at the end of it. So thank you. I guess I'm going to stop sharing. Is that right?
That's okay. Yes. I also have the chat open here. So if there are
cool.
That's okay. I can run around.
I'm going to let you moderate.
Exactly. So if there are questions online, you can ask them in the chat and we can read them out loud. But also questions here in the room, please join. You can talk loud. You can talk loud. Excellent.
I have two questions. So first of all, you might have mentioned it, but maybe you didn't pick it up really. What happens with the resin? Do you then detach it from the metals, or does it go into the metal? And how does it affect the metals? And then the second question is, so it absorbs the furnaces absorb all bad iron. Does that what then obviously the water still has iron in it? Doesn't get treated separately. So with the process we absorb the rare earths, and then you have a water that is still polluted and then gets treated separately, I guess, from that.
Okay, so the first question, I'm just repeating for the benefit of the online people. The first question is about the resins. What do we do with the resins? How do we recycle them? And the second question is, what do we do with the iron that's residual in the water? Okay, so the answer is yes, 100%. The resins are recycled. So what we do is it's actually a little polystyrene bead, and you fix that sulfonic acid onto it, and then it's got that little hydrogen atom stuck to it. So what you then do is you switch that out with the metal, and then afterwards you'll do an acid wash where you strip your metal off and you replace that hydrogen atom onto that sulfonic acid group, and then you can reuse that resin. So if I'm not going to go back in, it's too complicated. But it's about that switching. So you switch hydrogen with metal, then you put acid back in, and you can take the metal off and you can put the hydrogen back. The idea with that then is you've got the metal in its pure form, hopefully, if you do this correctly. So what you can do is you can have multi-stage columns. So your first column is more for like a cerium or or whatever the first one was, I can't remember now, neodymium, etc. So you can actually set up series of columns, and this ion exchange technology is quite good at that. These resins are reusable. If we are going to be really clever, we would ideally want to use secondhand resins from a different industry. So again, it's not politically correct anymore, but we have, for instance, cornstarch manufacturers where they make corn syrup from maize, and you have to purify that to a very high degree to make it food grade. So they use resins for the removal of the impurities coming from that process. So those resins are still very active before they need to be disposed by that food grade production facility. So we can reuse their resins at very low cost. Ultimately, we're going to be left with some microplastic polystyrene. We haven't engaged with what we do with those, but that's a later problem. The question about the iron is, yes, we're going to have iron. So in this project, what we had previously was we had access to something called basic oxygen furnace slag, BOF slag. So in our steel manufacturing, we have a lot of steel mills as well. We're a really big mining country. So we have a lot of steel manufacturing processes, and they make a slag. So for their steel production, they add limestone as a flux, and then you're left with this. You don't really. So Germany has a lot of slags. I don't think you guys have a lot of slags at all. So it's like a rock, and it's really alkaline. So if you mix this with water, the pH will go up to about 11 or 12 because you can actually dissolve lime from it. So we can then pass that water through like a lime, an alkaline, or a source of alkalinity, which we can extract from our basic oxygen furnace slag. We can titrate the two together and precipitate our iron into an iron oxide sludge of some sort. That's then particularly useful to sell back to the steel mills because that's basically rust. You know, they can use that. Or if we're clever, we can purify that and sell it to our wastewater treatment works as one of their reagents for precipitation. So the idea is that every single one of these steps, we have a valuable substance that nature has given us by virtue of us polluting the environment. And we're saying, well, let's pick them off one by one. Okay, is that good?
Thank you.
Cool. We have some
I see 3 questions online. I'm moderating here as well. So we have the first question by Marlene. I'm just moderating for you, Marlene. Thanks, Greg. Clear message of turning a liability/waste into an opportunity. It is encouraging that this can be done technically or economically. What is the political business interest here?
That's a good question. So I don't know the answer to it, I guess. And the reason I don't know the answer to it is that I come from a country with quite complex politics, and I tend to step away from them entirely. Partly the reason we did a lot of this work in the coal fields is that this is not a state-owned liability. They're often company liabilities with point sources of impact. And I much prefer that because you can see the polluter, you can access the AMD, and you can then generate something that's really site-specific. If you start engaging with the macro political environment, it can get really confusing very quickly. And it's the kind of confusing my brain is not very good at, is understanding macro political context. I'm much better with engineering and science. So I don't know the answer to your question. And that's exactly the same as I don't know how to deal with politics. So I'm going to just sidestep that.
If there's a question from the room, please say so or raise your hand. Otherwise, I'll continue online. From Doug, hi Craig, your breakthrough curves indicate that iron is controlling dynamics on the resins. Have you explored a pre-column removal of the iron so that your columns would have a longer life?
No, Doug, not at all. So the answer to the question is that we're still very much exploring how to get this right. Specifically, we're thinking about, so one of the things that's particularly nice is that we know that because we're removing the iron when we start to carry on load with the rare earths, we're not particularly distressed with the fact that the iron is coming on, because it seems that the affinity to the rare earths is better than the affinity with the iron. So, but I am exploring some other opportunities currently, in fact, with the University of Puerto Rico, where I want to have a look and see, are we able in any way whatsoever to do selective crystallization of the iron pre the columns, that we can actually get like a saturated solution and start growing iron. It should be possible from a thermodynamic perspective, but we're not sure of how that crystallization process would work. So that's what we're thinking about as a possible pre-step is, are we able to selectively grow iron crystals before we stick it through our columns?
Okay, I'm going to jump in with one more question for myself before I go to another one online.
Cool.
Lots of our mining waste is already stored somewhere, right? It's not always directly released into a river or another earth system in a mine day. Can we apply these resins, or is this way too big of a question?
So many of your waste locations will have a tow seep. So, you'll have a leach from your, not necessarily, let's just go to like a landfill site. You'll have a tow seep that will come out, and you have to extract that somehow, and you have to treat that because you don't want that getting into the environment. So I see this opportunity for all of these types of external seeps from, because typically things are not locked up. So that tow seep, you will then either pump back onto your tailings dam or your waste facility, or you will treat it and discharge it. So I think there's applicability in all of these contexts. Most lockup is not, unless it's in cement or something like that, it's generally not like mobilized. Yeah.
Thanks. Let me see, where are we at? I think we're at Margaret. I think you mentioned that you might want to include more ion exchange steps. Would they have a different resin, or would it be different color conditions?
Yes, to both. I think what we would want to do is we would want to test the different resins for the different rare earths and for different things. But so where this is complex is that you're ending up trying to design a bespoke solution for every context that you're in. And unfortunately, that's the reality of this century, I guess. And I think that's an appropriate thing to be doing. We're in a complex space, but we have a lot of complex tools that can help us. So we have machine learning and all of these things. So the idea would be that, yes, we would use different resins for different elements in different contexts, at different temperatures, at different flow rates. So, but we would have to obviously test all of those individually to see whether they would be working.
So the next step is to get some big mining company to collaborate with you, or what?
So, yeah, so we do have so we have mining companies collaborating with us, but they're not funding us in this context, and that's quite nice as well, because it means we're not necessarily beholden to them for a specific outcome. So for me, the collaboration is more around giving me access to your site, saying, can we have a look at it? Can we explore? And ultimately, I see these things as being locally operated companies that go into these tailings facilities areas, able to generate value on an ongoing basis, because the mining companies will typically not want to do this. And you could then charge them a toll, you could charge the mining house a toll fee for purifying their effluent, whilst you're making a revenue stream for maybe previously unemployed people. So there's definitely a potential for social outreach, but mining companies would have to get involved with that as well.
Short question by Sheridan, if I pronounce your name correctly, I hope so. Have you considered solvent extraction as a study?
And the very short answer is not yet.
And then a longer question by Sarah. Thank you for an interesting talk. Are the concentrations of REEs consistent across all ALE? For example, do rivers contain higher concentrations of REE? If so, what is controlling this, and can REEs be predicted?
So Sarah, I think that's a really interesting question. And I'm going to go out on a limb now, and I hope none of the environmental geologists, I think I'm correct on this. From what I understand, living organisms selectively partition rare earths from the environment, which means that you tend to have higher concentrations of rare earth elements in things like coal than in the general geology around us. They're ubiquitous globally. Certain countries have higher concentrations than others. For example, Scandinavia has quite high concentrations, hence all the Scandinavian names like holmium, etc. But typically, for example, fly ash, which is from coal burning, and the coal waste products have higher concentrations of rare earths than the general geological prevalence and the general geological abundance. And that's to do with the metabolic processes of organisms, particularly plants. The answer to your question is, are they different? The answer is yes, they would be different, and every site would have a different concentration. So we're seeing quite high variability across different sites. I don't know that it's possible to predict that up front because of the heterogeneity of your coal seams and your ore bodies wherever you are. And in fact, even beyond that, in the age of the Anthropocene, it's even more complex. We did some soil sampling in Johannesburg, quite close to my house, to see if we could get a non-mining impacted site. And it turns out it's so full of rare earths from auto vehicle catalysts that it's entirely contaminated. So even that question now is very difficult to answer because there's just widespread rare earth contamination. But what's quite useful about some of these sites is that these concentrations in our leaching liquors from the environment are at ppm level. So we might see 6 or 7 ppm. Now, if you're going to extract something like gold, you would be chasing rocks with 1 ppm at the moment. That's a viable ore body. So we're very much within the concentration ranges where this becomes economically viable, but we've never thought of doing it because this has always just been something to get rid of as quickly as possible. It's a waste product. Don't even think about it. So that's the idea, is we're saying a lot of these waste sites need to be reassessed, because in mining, about 90% of your cost is actually accessing the rock and crushing it. And most of that is energy to crush these big rocks down to minus 75 microns. It's a really energy intensive process. We're saying this has already been done. It's already there. All we have to do is take this liquid and start applying technologies in a careful way. But so your rivers would have it, but depending on what the geology is, they would be different. And I don't know what would be controlling this or how you would predict that. You probably wouldn't be able to predict that up front, but you could certainly go and do sampling campaigns. So thanks, that's a super question. Yeah. Cool.
Maybe you
does the mining process itself also affect the degree of rare earth elements in the product that is your starting point? Can you make any adjustments to make it more favorable to mine rare earth elements afterwards?
So the question was, does the mining process, can you adjust that to improve the extraction of rare earth elements afterwards? I don't know, because this is the sites we're specifically looking at on the east side of Johannesburg. This is coal mining, so your crushing processes are typically making small quantities of rock that are fairly, you want to burn it, so you don't want it as big lumps of coal going into your power stations. So coal is normally, it's crushed to about, I don't know, 2 or 3 centimeters, I guess, for sale. In the very, 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 very concentrated tailings facility that we had, what happened there was that was a lot of coal waste rock that was dumped on the side. So when you do this, you dig up the land, you have an open cast mine, you take all that waste rock and you put it to the one side. And they got a toe seep, which was acidic. So that's at the toe of the tailings dam, you get this thing, and they didn't know what to do with it. So they pumped it back onto the top of the coal waste rock dump. And that's actually why this site is so rich in these things, because it's been a 20-year recirculating heap leach process, because no one knew what to do with this environmental liability. So in that context, your mining processes are almost irrelevant, because you've had this continuous soaking through of this waste rock facility. If it were smaller, you would have different hydraulic properties of the waste rock, so it might take longer to get through, but you may have better leaching kinetics. But I'm not sure that I would want to selectively mine necessarily right now, unless we were aware of like a specific mineral that we were getting. So, sorry, for instance, for gold mining, you want, let me just think of the number, but 75 micron is the size of the rock particle that you want when you finish crushing and milling the rock, because the gold particles are so small that you need that small piece of rock in order to have your acids and your cyanide leach the gold out of it. So you're typically going to be targeting the size of your product rather than your waste product. And so in that instance, 70 minus, I think it's 90% minus 75 microns is the size of the crushed rock. So it's really small. But at that size, probably any other mineral is also exposed in that little silica matrix. there would be very little lockup in a grain of sand that small. And they call them slimes. It's very slimy. They're very, very fine sands.
I have a question from the room, otherwise I find one myself. Cool. Yeah. 2 weeks ago, I was at a lecture by Roland Doll about phosphate mining, where uranium plays a role as well. And you talked a little bit about uranium. How applicable do you think these Western techniques are in those type of mining? I don't know too much about it, so I want to pick your brain.
Yeah. So definitely you can use resins for uranium extraction and for purification, and it's done. We do it. We have a lot of, historically, we had quite a lot of uranium extraction works in that Wastewater and also the East Rand basin. So, and they would use resins and ion exchange processes to, they would use resins and ion exchange processes to purify the uranium for sale onwards. So there is some legacy around this. A lot of this was done pre-1994. So for those of you who know South African history, that was the year that we had the official first democratic government. Prior to that, we had some uranium isolation works where we could enrich uranium, and there's also speculation that we blew a thermonuclear device up out in the ocean somewhere, and we also have a nuclear power station. So all of that capacity has now been removed. We don't have it anymore, which I think we're the only country to voluntarily disarm globally. It's really an interesting and a very good statistic, I think. But we still have uranium, so we could still do that. But for me, what would worry me a little bit about that is we're also, we're a BRICS country. So some of our strong allies are countries that are not allies of other countries. And, you know, being non-aligned means that you're not aligned with anyone. So I would be very concerned about extracting uranium for any purposes right now.
So then I understand the reason why I asked the question was because from that lecture I saw that it was in artificial fertilizer production quite high because it wasn't always extracted. And that we're actually loading agricultural grounds now with uranium. So that's why I was wondering, would it be applicable in that sense? Yeah,
sure. I think it would be, absolutely. But again, you have to then think, what am I going to do with uranium once I've got this? So yeah, otherwise you just put it in the rivers and you give it to someone else.
Yeah,
it's worked so well for us so far.
Fair enough.
Yeah. Cool.
Okay, I want to thank everybody online and in the room for a great talk by Craig. Thank you, Craig. And I would like to skip applause.
Thanks. And oh, there's one.
I see there's one more hand raised. You can open your microphone, maybe. Nope, no question. Okay, I think then we conclude. Thank you very much, everybody, and see you on the next lecture.